You know that sound, right? That sudden pop, the lights go out, and someone says, "Oh, must be a short circuit." But what does that actually mean? We throw that term around all the time. So today, we're going to pull back the curtain. We're moving beyond the buzzword to really understand the powerful and pretty dangerous physics at play. All right, just a quick heads up before we dive in. This is our deep dive into the science of a short circuit. We're getting into the real nitty-gritty. If you're looking for more of a basic introduction, we actually did a great explainer on that already, so you might want to check that one out first. For everyone else, let's get into it. So, in a perfect world, electricity is, well, it's beautifully behaved. It flows from a power source, like a battery, follows a very specific path, goes through a device that does some work, we call that a load, like these light bulbs, and then it travels right back to where it started. It's a perfect continuous loop.
But then this happens. The power just cuts out. The bulb isn't broken, the battery's still good, but the light is gone. What's going on? This is the whole mystery of a short circuit. See, it's not about a part failing. It's about the electricity itself making a totally different and much more dangerous choice.
So here's our roadmap for today. First, we'll talk about the normal electrical highway. Then we'll explore that dangerous shortcut a short circuit creates and the science behind why it happens. We'll get into the hidden danger of a meltdown, meet the electrical bodyguards that keep us safe, and then we'll wrap it all up with 5 key rules to remember. Okay, first things first. Before we can understand what goes wrong, we have to be crystal clear on what right looks like. So let's start with the basics of a normal, happy circuit. At its heart, an electrical circuit is just a closed loop. Simple as that. The 2 key things you absolutely have to remember are continuous path and load. The path is the road the electricity travels on, and the load, whether it's a light bulb, a fan, your phone charger, that's the destination. The load is what does the work, and in doing so, it provides resistance, and that resistance is everything when it comes to controlling the flow. Okay, now let's throw a wrench into that perfect little system. What exactly is this dangerous shortcut we call a short circuit?
A short circuit is what happens when the current gets an alternate route, like an accidental bridge pops up. This new path lets the electricity completely bypass the thing that's supposed to be using the power. It's a detour that was never supposed to be there, and it has almost zero resistance.
Just look at this side by side. On the left, everything's working as it should. The current goes through the bulb lights up. Great. But on the right, see what happens when we add just one little wire across the terminals? The bulb goes completely dark. The electricity found that new, easier path and is now totally ignoring the bulb. And this is a super important point. The term short circuit is a little misleading, actually. It doesn't necessarily mean the electricity is taking a physically shorter route. It means it's taking an easier route, a path that effectively shorts out the load, cutting it right out of the loop. So, why? Why does the electricity even take this detour in the first place? Well, it all boils down to a fundamental law of physics. This right here is the golden rule. You can think of it like water flowing down a hill. It's not going to struggle to climb back up if there's a wide open channel for it to flow down instead. Electricity is basically the same. You could almost say it's lazy. It will always choose the easiest route available. Let's think about the 2 choices the current has here. The path through the light bulb has high resistance. It needs that resistance. That's what makes the little filament inside heat up and create light. The shortcut wire, though, that thing is like a brand new 10-lane superhighway with no speed limit and no other cars. It has basically zero resistance. So, faced with those 2 choices, which one do you think it's going to take? The electricity just floods down that open highway every single time. So the light goes out. Okay, what's the big deal? Well, this is where things get really serious. That easy path unleashes a hidden and, frankly, an incredibly dangerous consequence. Because there's nothing to slow it down, right? No load, no resistance. The amount of electricity, the current, flowing through that wire just surges uncontrollably. And we are not talking about a small increase here. The current can spike to hundreds of times its normal, safe level in a split second. And that surge kicks off a really dangerous chain reaction. First, you get the low resistance path, which leads to a massive, uncontrolled current surge. All that energy crammed into a tiny wire generates intense, crazy heat. Think of it like friction on overdrive. The wire's plastic insulation just melts away, exposing the live wire, which leads to sparks, and that can easily set fire to anything nearby. This is exactly how most electrical fires get started. So if our systems are this vulnerable, why don't our houses just burst into flames all the time? Well, back in the early days of electricity, they often did. And that led to the invention of our electrical system's personal bodyguards, designed for this exact scenario. Fuses and circuit breakers are your system's emergency brakes. They are constantly monitoring the flow of current. The instant they detect that massive, dangerous surge from a short circuit, they spring into action. They physically break the connection, shutting the whole circuit down and stopping the flow of electricity long before the wires can get hot enough to cause a fire. They're like little sacrificial heroes, designed to fail safely in order to protect everything else. Okay, we've covered a lot, so let's boil it all down to 5 simple core ideas to make sure this all sticks. Let's run through it. Number 1, electricity always needs a complete path. 2, it will always prefer the easiest path it can find. 3, a short circuit is just an accidental shortcut that bypasses the main job. 4, that bypass causes a massive, dangerous surge of current and heat. And number 5, our fuses and circuit breakers are the essential bodyguards that stop that surge in its tracks. Look, understanding this isn't just theory. It's about being safer in the real world. A cord with worn-out insulation is literally a short circuit just waiting to happen. So I'll leave you with a question to think about. Knowing what you know now, what's one spot in your house, maybe behind the TV or under your desk, where you might want to take a closer look at your electrical cords? And of course, we have to end with this. Knowing the science is great, it's empowering, but electricity is not something to mess around with. If you see frayed wires, if you have any electrical concerns at all, please just call a qualified professional. Stay safe out there and stay curious.